Having introduced the various types of critical points that we typically encounter, maxes, mins, and saddle points, we then go to the challenge of identifying the type of critical point we found when we only have a formula for the function, when we do not have a contour diagram to work with. Just remembering the first term material, we had two choices when we looked to classify a critical point. We could use a first derivative test, or we could use a second derivative test. And again, the first derivative test said if f prime of x is less than 0, and then we have 0, and then f prime of x is positive, that told us that the function was decreasing, then hits a zero value, zero slope rather, and then positive slopes, and so that was a local minimum. How does that generalize to multivariate functions? Well, let's take our quick critical point stuff here that we had, and let's put a saddle point in here, so we have some kind of saddle point like so. If this is our x and y directions combined, ask yourself, well, the slope is less than 0. The slope is negative. Well, the slope in what direction? We no longer have just a left and a right direction. We have an infinite number of directions we can go in. And certainly, if this was, let's say it's a local max, 0, 1, 2, if this was a local max, well, we could say, oh yeah, all the directions point downhill. The slope's negative in every direction, no matter which direction I go in. But then you have to test them all. It's possible that there's maybe some little window, some little narrow part where the slopes are positive, and you'd have to find that. Likewise, in a saddle point, you could say, well, it's going up in this direction, it's going up in this direction, it's going up in a whole bunch of directions. But there's a couple of directions where if I follow that path, it would go down. We would have to somehow systematically search for the direction of the function or the surface in every possible direction around the point. It doesn't have to be just x and y, it could be any direction. We do not have the time for that. That is not something that's really feasible. So the fact that we have too many directions around a point means that the first derivative test, which I did, it was my favorite for one variable functions because it's clean, it's easy, doesn't involve second derivatives, it always tells you what's happening. It was the best single variable derivative test for classifying a critical point. Unfortunately, it does not generalize to multivariate functions in any way that we can make use of. So, thank goodness, we have the second derivative test. So the second derivative test, as a quick reminder, is about the concavity around a critical point. If we have a critical point that's a local min, we know it's a local min in one variable because it's concave up. Well, we've talked already about concavity in our multivariate functions as well, and we can talk about second derivatives and calculating those. So this looks like a potentially profitable way to tackle the idea or the challenge of classifying critical points when all we have is a formula. So here, in all its glory, is the technique or the process for applying the second derivative test. So first, find a critical point. This only makes sense at a critical point. We're going to define a constant called d, or a value called d, and as you might expect, we involve the second derivatives, but notice that there's three possible second derivatives when we're talking about a function of two variables. We've got the double x derivative, double y partial, and then the mixed partial x and y. So here's the hard and fast rules. What you can do is memorize this, taking into account the possible shapes we're discussing here. One's local minimum, one is a local maximum, and one is a saddle. What I like to think about this when I'm trying to memorize this formula, though, and you do have to memorize it, it's basically a test that you need to understand and know. There's a really nice structure to this system here. It looks complicated, but if you think about where these values are coming from, it'll make a lot more sense. Let's talk about the local minimum. In two directions, or in all directions technically, but it's certainly in two cardinal directions. This is concave up and concave up. And what that means, we're going to ignore this term here. It's basically a correction term. We'll see how that plays out. But let's say we just talked about the x and y directions. We would have xx derivative positive and yy's derivative positive. If we multiply those two, which is what this d value does for us, we multiply those two quantities, we would get something positive. So fxx times fyy is positive. The product is positive. Well, that's one of these two cases here. If that d value is positive, and we can read this as one of the concavities is also positive, well, what this is translating to is both concavities are the same. Let me just point that out here. If we talk about the concave down and concave down in a local maximum, this would be negative second derivatives, but if we combine them, we would get a positive value because we have a negative times a negative. So we get a positive value. So what these two scenarios share in common is that if we multiply out the concavity in both directions, they're either both positive, meaning the product is positive, or they're both negative, again, meaning the product is positive, and that would make our d value positive. We'll sort of brush this under the carpet for the moment. And then, so what this d being positive means is that both concavities are the same. Once we've said, oh, the d value is positive, so I'm talking about either all concave up or all concave down, then we just look at any one of them. And we could look at fyy as if we wanted to. Usually the rule is written with fxx because it usually happens to be the first thing on our page. But if one of them is going to be positive, then we know that both of them are going to be positive, and so we've got a concave up scenario that describes a local minimum. Likewise, if we had a negative concavity, so something concave down, but the product of both concavities is positive, so they're both the same, both concavities are the same sign, then we'd have a local maximum, like here. And the d less than 0, well, think about the concavities there. We've got one concave up and one direction that's concave down, so it's a mix. Again, that idea, it's somehow a local max in one direction and a local min in another. When we multiply the second derivative signs, second derivatives are concavities, one would be positive, one would be negative. So the product being negative means you're somehow mixing concavities, and that translates to a saddle point. Last but not least, if we happen to get an unlucky case, and you'll see some of these in your assignment problems, where this value that we calculate ends up being 0, this is the downside of the second derivative test, we have no information. The second derivative test gives no information. So that's a little unsatisfying, but it is pretty cool that we can classify all of these different shapes by thinking about the concavities and seeing how they're played out in the surface and how they play out in the algebra, looking at the second derivatives of our function. Now, oh my goodness, there's lots of connections here. I don't want to go into too much detail because not everyone's taking algebra or has taken algebra. If you're looking at this xy term here, I did brush that explicitly under the carpet as we did this. The reason for this is sometimes a function might not be aligned with the x and y axes in particular. It might have, it might be rotated or something. This xy partial derivative is what corrects for the possibility that it might be concave up in both the x and y directions, pure x and y directions, but then concave down in some other angle. For those who've been have done any linear algebra, if you want a shortcut for this calculation, you can take the determinant of the matrix of second derivatives. I've got a second derivative with respect to x, one with xy, xy, and yy. And if you've ever seen a determinant before, it's the product of the diagonal minus the product of this, or the anti-diagonal. That's exactly what we're calculating here. There's some lovely connections to Taylor polynomials. If you look at the values here, these are all values that appear in the second degree Taylor polynomial that we saw earlier in the course. This, I would say, is the introduction to vector calculus, which is a course, there's two courses at Queen's, 221 and 280, that introduce and expand on these ideas and really start combining algebra and calculus and vectors into looking at three-dimensional shapes and flows. And physicists love that kind of stuff. Mathematicians love it. Other people should love it, but sometimes you don't get the chance to study it. Anyway, that's enough for now about this lovely discriminant or second derivative test. Key thing for those who are just looking to survive and get through, this D, don't think of it as a D as a formula, or you can, but it's not as easy. Think of it as the product of your two concavities. If it's positive, your concavities are the same. If it's negative, immediately your concavities are different, and so you have a saddle point. If the concavities are the same, you just look at one of the concavities, it doesn't matter which one. If one of them's positive and they're both the same, they're both positive, then you're at a local minimum. If your concavities are the same and they're both negative, you've got concave down in every direction, you're going to be at a local maximum. And that's the easy way to remember that test.